In this video, I will show you the basics of steady-state capacitive circuit analysis. So in steady state, we have constant voltages and currents. So if you remember from the previous video, that means that the current through any capacitor in steady state is zero. So if you don't remember that, go take a look. So the principles when analyzing a circuit in steady state with capacitors is first you draw the steady state circuit and then you get any values as desired from the steady state circuit. So in this problem, we want IS and VC, assuming that the switch has been open for a long time already by time zero. And then we're looking for the same values at time infinity, so the switch will have been closed for a long time. And so the key words for a long time indicate that we are looking at steady state conditions both at time zero and of course time infinity. That's a long time, right? So steady state in both cases. So let's start with the time equals zero case. So the first thing is to sketch the circuit. So with the switch open for a long time at time zero, R2 doesn't play a role at all because no current can flow through it. Voltage across at zero. And so that's the circuit, but that's not quite the steady state circuit. Recall that in steady state, the capacitor acts like an open circuit. So we'll put here VC. And we'll just designate the nodes A, B, C. So what we really want is the voltage VBC, and we want this current IS. Well, here it's already apparent that IS equals zero because it can't flow at all in the steady state circuit. And then VC equals VBC. And then we can get this from a Kirchhoff's voltage law analysis. So we know that if IS equals zero, then the voltage drop here is zero. So we're left with the following KVL equation. Going around the loop in a clockwise direction, we have negative Vs plus 0 plus Vc. That's equal to 0, so Vc equals Vs. So we have our two results for time 0, so no current, and the voltage across that capacitor is just Vc. At time equals infinity, R2 plays a role now. So let's sketch that circuit. And then I'm just going to skip straight to steady state, and we'll draw the open circuit for the capacitor. So what we can see here is that if we designate the nodes A, B, C, again VC is VBC, capacitor voltage is VBC, and if we can find VBC, then we get VC. That's the whole idea. And if you pay attention to this current IS, well, R1 and R2 are connected in series because at node B they are connected, but there's no other current carrying connections there. So this is also IS going through R2. And so we can get the voltage from B to C. It's just the voltage across R2. Actually, an easier thing than this, right? We don't know IS at this point, but we can just use a voltage division because R1 and R2 are in series. So we'll put here Vs like this. So if we know Vs, we know R1, R2. That's enough to get us Vc. So since I didn't specify any numbers, I won't write those out. But we also have enough information to get IS. Right? It's the voltage across the R1-2 series divided by the resistance R1 plus R2. And so we know the voltage source, we know the two resistors, that's enough to get us IS. So in this case, I've shown you how to do a steady state analysis for a simple circuit. I didn't plug in any real numbers for you, but you could do that if we gave you numbers. And so here I've just done it symbolically. So again, the main steps are Draw the circuit in steady state. Do that. Don't skip it. It helps you make sure you know what's going on and analyze it properly. Then you get the steady state values as desired, just like I showed you. Sometimes you want a current, sometimes you want a voltage, maybe it's a power even. But steady state analysis is pretty straightforward. Just follow the steps, look for the keywords long time, and you should be all right.